You, ladies and gentlemen, for coming to participate in this evening with us. So let me start with the introduction. Good evening to Dr. Kanjana Amarasegara, IESL committee members and fellow engineers. Let me start the meeting with acknowledging traditional landowners as our tradition. In the spirit of reconciliation, the IESL NSW chapter acknowledges the traditional custodians of the country throughout Australia and their connections to land, sea, and community. We pay our respect to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander peoples today. First of all, let me thank Dr. Kanjana Amarasegara for accepting our chapter's request and delivering this valuable lecture for our members. It is the time now and privilege to introduce Dr. Kanjana Amarasegara to our audience. Dr. Kanjana obtained her electrical and electronic engineering degree from University of Pennsylvania with a first-class honors in 2011. She obtained her PhD from University of Wollongong in Australia, specializing in electrical power systems in 2017. Her PhD thesis focused on investigation of voltage stability in wind-rich electrical power system. Kanjana has both research and industry experience, specializing in the areas of power system analysis, grid integration of renewable power generation, and transmission network planning. During the past 6 years, she held position in power utility and consulting industry in Australia, where she involved in grid integration of a number of large renewable generator connection projects in the national electricity market. Currently, she works as a senior engineer in Transgrid, Sydney. She is passionate about contributing to the secure and smooth transition to high penetration level of clean and renewable energy in power networks. These new forms of generators introduce new challenges in maintaining the power system, security, and reliability. For a smooth transition towards the power system with renewable energy, alternative methods will have to be utilized to provide many of the grid support services, such as inertia system strength and frequency control. These techniques quite differ with the traditional power networks with large spinning generators. In this presentation, the challenges and opportunities associated with the connection of large utility scale renewable power generators will be discussed. In this presentation, the generator connection process and techniques requirements applicable to renewable energy generator connections in national electricity market will be discussed. I am very confident Dr. Kanjana's presentation and many of her findings may suitably adapted to deal the current electricity crisis in Sri Lanka. Let us welcome Dr. Kanjana Amarasegara to deliver her valuable presentation. Thank you. Dr. Kanjana.
Hello, everyone. Thank you, Soti, for the kind introduction. I would also like to thank IESL New South Wales chapter and the committee for the invitation and the opportunity to present today. I would also like to thank all the attendees who joined this meeting today. It is my pleasure to present to you all today. So, as Soti mentioned, the title of today's presentation is Grid Integration of Utility Scale Renewable Power Generation. The main motivation for me to do this presentation today is actually to support anyone who would like to pursue a career in this area particularly young engineers. So I think this presentation will be helpful to anyone who would like to pursue a career in this area. So with that initial notes, let's move on to the topic now. So this discussion is about electricity. So electricity is a hot topic in Australia these days. There are a few reasons for that one. The main reasons are due to some things happen in Australia during the past few months. But one of the key reasons that we all are aware of is the increase in electricity costs. So it is expected that by increasing the renewable share in our power system, we can reduce our electricity cost in the long term. So in Australia, we are currently in a very rapid transition towards a renewable rich network, and it is supported by various government policies as well. So when we talk about renewable energy, there are two categories in that. The first category is utility scale large generators, or utility scale large renewable generators. The second category is DER, which means distributed energy resources. They include small installations and things like rooftop solar PV that you might have in your houses. So the focus of today's presentation is the first category of out of these two categories, which is the utility scale renewable power generation. And I will continue with the discussion in the context of national electricity market in Australia, which is the electricity grid in the eastern coast of Australia. So this is the overview of the presentation today. I will start the discussion with giving you an overview of the current energy mix in the NEM, and then I will discuss why renewable energy generators are different compared to conventional generators that we had in the system, and what are the challenges and potential opportunities or potential solutions to those challenges. And in the last part of the presentation, I would like to briefly talk about and give an overview of the generator connections process applicable in the national electricity market, or NEM, in Australia. So as I mentioned before, I thought of starting the discussion by giving you an overview of the current energy mix in the NEM. So these details, I have taken these details from Australian Energy Market Operator, or AEMO's Integrated System Plan document. We call it AEMO's ISP document, which was published very recently. So these figures are extracted from that document. According to that document, the total installed capacity, total installed generation capacity in NEM at this stage is around 60 gigawatts. The current installed utility scale variable renewable energy capacity is about 16 gigawatts. And we also have got about 15 gigawatts of installed distributed PV capacity. And in 2021 and 2022, the total share of renewable energy out of the total annual generation is about 32%. And when we talk about the instantaneous renewable penetration levels, NEM recorded the highest instantaneous renewable penetration level of about 61.8 in last year, in late last year, in 2021. So this is where we are in terms of the current energy mix in the NEM. In the next slide, I would like to talk about the future forecast for the NEM. Again, I extracted this figure from the AEMO's ISP document. AEMO's ISP basically looked at the Australian power system, or NEM, up to 30 years, up to like 2050, under various scenarios. From those different scenarios, this step change scenario is considered as the most likely scenario. So I selected this figure for this presentation today. So what we can get out of this figure? So the first thing that we can see is it is expected that at least 60% of the existing coal generators will retire by 2030. And it is also expected that the variable renewable energy capacity in the network will triple by 2030. And one more conclusion in that was at least half of the houses in the NEM will have solar PV by 2032. As you can see, we also expect that the total electricity delivered will be doubled by 2050 as well. So the reason why I wanted to include this figure in this presentation is to show you the scale of transition that we are expecting in Australia in terms of renewable power generation. So with that initial introduction to the NEM, I also thought of giving you a brief introduction to the national electricity market in Australia as well, because I'm planning to continue the discussion in the context of NEM. So there might be people who are not familiar with NEM. So I thought of giving a brief introduction to NEM. So NEM is the electricity network of the east coast of Australia, and it spans from Tasmania, South Australia to North Queensland across 5 states. And there are interconnectors between each state, and it is considered as one of the largest interconnected electricity systems in the world. AEMC, or Australian Energy Market Commission, develops the rules for the operation of the NEM. Australian Energy Market Operator, or AEMO, is responsible for the day-to-day operations of the energy market. And we also have a body called AER, Australian Energy Regulator, who enforces the rules in NEM. In each state, we have TNSPs and DNSPs. TNSP means Transmission Network Service Provider. Usually, each state has a has one TNSP who looks after the transmission network, and few DNSPs, Distribution Network Service Providers, who looks after the distribution network up to your household. Then we have retailers in NEM who will buy electricity from the wholesale market and sell to customers. So this is a very brief summary or introduction to NEM because I'm planning to continue the discussion in the context of NEM. So starting the discussion on renewables, the first question is, why renewables? I think there are two main drivers for to have more renewables in the network. They are mainly because renewables are cheap and clean. So we all want to reduce the greenhouse emissions to reach net zero emissions. And we also want to reduce the reliance on fossil fuels. So the main two drivers for a renewable rich network is because they are clean and cheap. And in the next slide, if it is clean and cheap, what is stopping us from going into a high network with high renewable penetration levels? What are the challenges? So in this slide, I want to explain the differences of renewable generators compared to conventional power generators. So in conventional power systems, the generators that we use are synchronous generators. And the conventional, the operation and the dynamics of conventional power networks are also designed around synchronous generators. However, these renewable generators, they use power electronic converters and small asynchronous generators. Usually these power electronic converters decouple the traditional coupling we had between the mechanical dynamics of the machines and the network electromagnetic dynamics. So that is one key difference in renewable energy generators. So the other thing is with synchronous generators, usually they used to be large spinning machines. However, these small machines or completely power electronic based generators, they have no or little contribution towards system inertia. Then renewables are intermittent and have a limited predictability, and they are not dispatchable. In other words, we cannot turn them on as we want. So these different characteristics of renewables compared to conventional generators impose lots of challenges when we try to increase the renewable share in the networks. And so when we try to achieve 100% renewable penetration levels in the networks, I think there are two things that we need to focus on. The first category is how to manage this variability and uncertainty, and how we can supply the demand, including the peak demand. So I think supplying the demand during the daytime when sun is shining may not be as challenging as supplying the evening peak demand. In Australia, usually the peak demand happens in the late evening these days when sun ramps down and when people return to houses and start turning on their appliances. So supplying the peak demand is a challenge, and managing the variability and uncertainty is also a challenge. Then when we talk about power systems or an electrical network, it's not just about meeting the supply and demand. For the secure and reliable operation of the power system, it needs a number of other network services as well. Usually in conventional power networks, synchronous generators used to provide these network services. So when we try to move towards 100% renewable penetration levels or try to increase the renewable share in networks, we need to find out alternative methods to supply these network services. In the next few slides, I'm planning to discuss few of these network services in a bit more detail. So these are the key services that I'm planning to discuss in this presentation, and these services were traditionally provided by synchronous generators in conventional power networks. So the first network service is system strength. System strength is defined as the ability of a power system to maintain its voltage waveform. So the normal waveform, voltage waveform of a power system will look like something like this. And the system strength is proportional to the fall level of the location. Usually, if the fall level is high, we say the system strength is high. If the fall level is low, we say system strength is low. One of the characteristics of a system with low system strength is we see large voltage changes for any change in power flow. For example, if we switch a capacitor bank or an inductor in a network with low system strength, we will see large voltage changes. I have used these two figures as well. This shows the difference between a fault response in a high system strength and low system strength network. As you can see in this scenario with high system strength, after the fault, voltage have recovered back to their stable pre-disturbance voltages. But in this low system strength condition, you can see even during the fault, we see large step changes in voltage, and even after the fault, voltage hasn't recovered back to its balanced voltage levels. So this is something that could happen in a system with low system strength. And in Australia, these days, we mostly see these system strength issues in remote parts of the networks, which are far away from the existing synchronous generators. But as we move towards higher and higher penetration levels of renewable generators, I think we will start to see these issues in everywhere, basically. So then I wanted to discuss what can provide system strength services. In traditional power networks, synchronous generators, it could be hydro, coal, or gas, they used to provide system strength services. Even synchronous condensers can provide these services. A synchronous condenser is basically similar to a synchronous generator, but it doesn't have, it's a synchronous machine, it doesn't have a prime mover. And in the next part, I also wanted to show you the difference between the fault contribution of a synchronous machine and an inverter. So these two figures are basically the first figure is the symmetrical short circuit current of a synchronous machine, and this is the DC component. So as you can see here, in a synchronous machine, they have a very high short-term capacity, and as you can see, they can provide like up to 5 to 6 times of the rated current for like up to few cycles, and like 2 times the rated current for like up to few seconds, and it decays faster, but this short-term overload capability is really helpful. But if we compare a synchronous generator to a similar sized inverter, usually they have a flat response. Sometimes they claim they have some contribution. Even if they have, it's very, compared to a synchronous generator, it's quite small, and it's for a very short duration as well. So this is another key difference between synchronous machines and inverter-based generators. Then in this slide, I wanted to discuss what happens to the system strength with inverter-based generators. 99% of the inverter-based generators that we have in Australia right now, they use a technology called grid-following inverters. So what it does is, these grid-following inverters, they try to follow the grid voltage waveform. So they have a device or a control system called phase lock loop, or PLL, and it tracks the grid angle, grid phase angle, and basically the inverter tries to follow the grid voltage waveform and try to synchronize to that one. And what happens is, when the system strength is low, as I mentioned in the previous slides, there will be large changes in system voltages, and it can result large changes in the phase angle. So when the PLL tries to track this phase angle, due to these very large variations, it might not be able to track it properly, and it can lead to instability. So this is one key reason why conventional or widely used grid following inverters can lead to instabilities in systems with low system strength. And usually for stable operation of these grid following inverters, they need adequate system strength. So basically when we talk about system strength, we usually refer to this concept called short circuit ratio, which is defined as the ratio between the fault level and the plant MVA capacity. So usually inverter-based grid following inverters, they can operate down to like SCR of 3 without any issue, but when the system conditions goes below like SCR of 3 under very low system strength conditions, they struggle to operate stably. So then again, in this slide, I wanted to discuss what happens when there's low system strength. I think I already covered some items. Basically, systems could lead to undamped voltage or power oscillations, and even protection equipment might go to maloperation or even fail to operate. The reason is the protection equipments in traditional power networks are designed around fault levels or fault currents. So basically they operate based on fault currents, but when the system strength of the networks is declining with the increased penetration levels of IBR, it could lead to maloperation of protection devices. Then, as I mentioned, for switching of reactors or capacitors, it could lead to large step changes. It could lead to generators and other dynamics plants to instability, and it could cause issues with generator fault right through. So these are the issues when system strength, under low system strength conditions. Then the question is how system strength can be managed with high penetration of renewables. So as I mentioned before, in conventional power systems, synchronous machines used to provide these services. And if we are trying to go towards a renewable-rich network, what are the alternative ways to provide these system strength services? As I mentioned, first one I have in the list is synchronous condensers. They are a synchronous machine, so they are synchronous machines, so they can provide system strength support. And in fact, in Australia, we already have some synchronous generators already in service to provide these services. Then the second item is grid forming inverters. So I will discuss this concept called grid forming inverters in a bit more detail in one of my later slides. Basically what that means is, compared to grid following inverters that I explained in the previous slide, these grid forming inverters, they don't need adequate fault levels to operate. So they can stably operate under low system strength conditions. Why is that? I'll explain that one in a later slide. The third item I have is advanced site-specific controller tuning. So sometimes by advanced site-specific controller tuning, we can manage some controller interactions up to a certain level, but it might not resolve all the issues, but it can be used to manage issues up to a certain level. The last item I had is development of new network infrastructure. So as I mentioned, usually we see these issues in the remote part of the network. So if we develop new network infrastructure, it could increase the effective, reduce the effective electrical impedance. So because of that, it could also help. Then in Australia or in NEM, we already have a framework to manage the system strength issues caused by generators. I thought of giving a brief overview of this framework as well. Right now, we are going through a rule change. Actual rule change has been approved, and as a result, there will be new guidelines applied in NEM after March 2023. But here I'm explaining the current framework, which is still applicable. So basically, this framework is coming from System Strength Impact Assessment Guidelines published by AMO in 2018. So for generators, it shows us a two-stage process. So in the initial stage of a generator connection project, the network service provider or NSP develops a document called a preliminary impact assessment. So in preliminary impact assessments, we basically look at two things. First thing is, it calculates the minimum short circuit ratio applicable at the connection point of the generator. I mentioned what's the definition of short circuit ratio. Basically, it is the ratio between fault level and the plant MVA capacity. So basically, we are calculating the minimum fault level applicable to that connection, at the connection point. Actually, in the real calculation, we use a concept called available fault level, but I won't go into that details. But in summary, what it looks at is what's the minimum fault level and what's the minimum SCR at the connection point for that connection. It is to see whether they can stably operate at that condition. So that's the target of the first criteria. The second criteria is when a new generator tries to connect, there are a number of other generators in the surrounding network as well. And these generators are also grid following generators usually, and they need adequate system strength to operate. So we also check the impact of the new generator on these existing nearby generators as well. And this PIA, or the Preliminary Impact Assessment, is a very high-level screening assessment. Actually, it only looks at this minimum fault level and the SCRs. And based on that, it tries to identify the likelihood of any adverse system strength impact. So it's like a screening process. If the SCR is quite high and there are not many plants around, so usually we can say it's okay. But if it is not okay, those generators will have to go to a second stage. This step happens later in the connection process. It is called full impact assessment. So later in the connection process, if the PIA concludes that the FIA is required, later in the connection process, the network service provider will do more intensive assessments using wide area EMT models under various conditions and looking at various contingencies. So in them, the EMT tool that we use is PSCAD. So this FIA requires intensive PSCAD studies, and it will identify whether there are any adverse system strength impact. So, so there could be two conclusions at the end of the FIA, that there's no system strength impact, or the second one is there's adverse system strength impact. If there's any adverse system strength impact, then the generator will have to provide some remediation. So the remediation could vary depending on the scale of the issue. It could vary from simple protection scheme to installation of a synchronous condenser or another development. So depending on the scale of the issue, they usually have to come up with the remediation method. That's how the system strength is currently managed in the NEM. Then I already talked about grid forming inverters in one of my previous slides. So I thought of giving you a brief introduction to grid forming inverters as well. It is an emerging concept, and I think even in the NEM we are still trying to learn many things about that. But I just wanted to give you an introduction. And in Australia, I think we have about at least 2 in-service grid forming inverter projects at this stage. So basically, this diagram tries to show you the difference between a grid following and a grid forming inverter. So in a grid following inverter, it demonstrates a characteristic of a current source. So basically, as I mentioned in the previous slide, they have a device called PLL, which tracks the grid angle, and it tries to inject some currents to deliver the required power, and in general it demonstrates a current source behavior. But grid forming inverters, they demonstrate a voltage source behavior. So it is like a synchronous machine. They can set their own internal voltage waveform, and they can operate independently of other generations. So it can form its own grid, in other words, and it's like a voltage source similar to a synchronous generator. So compared to a grid following inverter, it doesn't try to follow the grid voltage or doesn't rely on the PLL measurement. So it is the key difference between grid following and grid forming inverters. Then what are the advantages of these grid forming inverters? So as I mentioned, they can stably operate in weak grids. And the second advantage is there are ways to provide synthetic inertial support using these grid forming inverters. Basically, they try to mimic the behavior of the synchronous machine within the controller and try to provide a synthetic inertial response. So that's another advantage. And as they are like synchronous generators, which shows a voltage source characteristic, and it can form its own grid, they can stably operate under islanded conditions as well. For example, let's say there's a fault in the interconnector and one part of the network gets separated without any synchronous machines in that part, then grid following inverters might struggle to operate, but the idea is grid forming should be able to operate stably. And it is also expected that these should be able to provide black system restoration services, in other words, to energize a local network during a black system event. So these are the key advantages of that grid forming technology. So we were discussing about the network support services. So next network support service that I wanted to discuss is inertial support. Inertia is an inherent quality of the power system which reduces the rapid changes of the frequency or rate of change of frequency. So I again took this analogy from AMO to explain the concept of inertia. So what we have here is a wombat running on a wheel, and let's say suddenly wombat stops running, but then the wheel will still keep on moving for some time. It's due to wheel's inertia. Similarly, in power systems, this inertia is provided by synchronous generators. And basically, synchronous generators release stored kinetic energy instantaneously to the grid to reduce the instantaneous rate of change of frequency. And usually other frequency control services in the network, such as governors or primary or secondary frequency control, comes in later to manage the subsequent frequency stabilization. I will explain this a bit more with this figure. So as an example, let's say a generator trips in a network and then frequency started dropping. So with inertia, what it does is it controls this initial rate of change of frequency. So it holds the network during that initial period until other frequency control services manage that frequency disturbance. But that initial rate of change is controlled by system inertia. And what happens is when the non-synchronous generation increases, we could see large drop-off or rate of change of frequencies. And what it means is sometimes even before other services can start responding to that, system could go to instability if we don't manage the rate of change of frequency. So this is about inertial support. Then again, we have the same question. If in traditional networks, these services are provided by synchronous machines, what happens when it comes to the renewable networks? So here I wanted to discuss two concepts. The first concept is synthetic inertia. As I mentioned, things like grid forming inverters can provide synthetic inertia, and it is faster. However, there's the second concept called fast frequency response. Again, but it depends on the frequency measurement from the network. So basically, it gets the frequency measurement from the grid network and tries to respond to that with the appropriate active power. But usually, grid following inverters also can provide these services, but it depends on whether they have any headrooms or batteries usually can provide fast frequency responses. services. And the third concept is even synchronous condensers. As I mentioned, synchronous condensers can provide system strength services as well. They can also provide inertial support as well, and we can add some flywheels to change as well. The next network support service I wanted to discuss is frequency support. So as I mentioned, Inertia will manage the initial rate of change of frequency during frequency disturbance, but other frequency control services will help arresting that frequency change and bring back the system back to 50 Hertz. So usually any generator can provide primary frequency control services, but the main problem with renewables is there's no headroom. So if there's headroom, they can provide those services. So usually batteries and other services will have to provide these services when we go to renewable rich networks. The next service is islanded operation and system restoration. So basically, as I mentioned before, if there's any islanding condition, without islanding means there's no synchronous machine. And the second item is black start. It is the ability of a generator to restart the power system to recover from a blackout. Usually these services are provided by synchronous machines. Even right now, I think these services are normally provided by synchronous machines, but going forward, it is expected that these other emerging technologies like forming service inverters can provide these services. But as far as I know, at least in Australia, I don't think that this capability is tested in the network, but I'm sure it's been tested in environments like microgrids. Then I already mentioned battery and other energy storage devices few times. So they play a key role in the transition to high renewable penetration levels. So because basically we should be able to store the energy to supply the demand, and we also need storage to manage any variabilities and uncertainties of the variable renewable energy. And also, let's say in Australia during the daytime we have lots of sun, but the demand could be less. So we need to have storage devices to store this energy when it's available and dispatch when it's not available, for example, in the late evening. So storage is it's a very important factor when we talk about moving towards high renewable penetration levels. And when it comes to energy storage, there are a number of ways. It could have a number of forms. It could be utility scale batteries, it could be household small scale batteries, community batteries, or even electric vehicles. And pumped hydro, things like pumped hydro is also put under the same category. There could be other ways to store energy, but I just included these three, which I think is already used in power systems around the world for energy storage purposes. Then in next few slides, I thought of discussing a few other important factors in this transition towards renewable rich networks. This first one is voltage control. So in traditional networks, usually the characteristics of synchronous machines really helped us to maintain the voltage stability, particularly this high short-term capability of synchronous machines helped us in maintaining the voltage stability. And as I mentioned before, under low system strength conditions, managing the voltage stability with high renewable penetrations could be challenging as well. But the good thing is usually inverter-based generators can provide reactive power capability and voltage control capabilities. especially reactive power capability. If they are properly sized, they can provide reactive power capability, and if they operate in voltage control, we can use that reactive power capability effectively to manage the system voltages. The next point is, when we move towards high penetration levels of renewable energy, strong interconnection between the regions is quite important, because then energy can be transferred between regions without many issues. For example, in Australia, we have a very long network, so sometimes we might have lots of wind generation in South Australia. Sometimes we might have lots of solar generation in Queensland or New South Wales. So if we can reduce the constraints in the interconnectors, or if we can improve those, it can help us in managing this transition towards high renewable penetration levels. The next factor I wanted to discuss is the importance of modeling. So accurate modeling is very important in this to make correct planning decisions. And when we talk about modeling, there are different types of models. Basically, I have selected these two types, RMS types models and EMT type models. We usually use PSSE as our RMS tool in them, and PSCAD as our EMT tool. So for different types of studies, we need to choose the appropriate models. Like for a load flow study, I mean, we can use our RMS model, but if we want to assess the real converter behavior and the system strength, we need to go for more accurate models like EMT. And the other important factor is generator model validation is also important. What I meant by generator model validation is validating the model performance against the actual plant performance. So we are in the last part of the presentation now. In this last part of the presentation, I wanted to give a brief introduction to the generator connection process applicable in national electricity market. This generator connection process is given in National Electricity Rules, or NER, and Chapter 5 of NER focuses on the generator connection related rules. And this generator connection process comes from this Chapter 5 of the NER. And the same chapter also includes the technical requirements for generator connections. So basically, these are the grid codes. In Australia, it is called technical requirements for generator connections. Basically, clauses S52, 52, 528 of this NER, Chapter 5, lists the technical requirements for applicable for a generator connection. And usually, for any generator, when they connect, they have a document called Generator Performance Standards, which includes these technical requirements that they have to meet. I would have time to go through these technical requirements in this presentation today, but the reason why I included this is if someone is interested to know what Australia's grid codes are, this is where they are. If you are interested to know more about that. Then one more point is, when it comes to these grid codes, basically the generator connection process is the same for both synchronous generators or synchronous or renewable generators. But when it comes to grid codes or the technical requirements, sometimes for some technical requirements, we have different expectations for synchronous and renewable generators. So in the next slide, I wanted to discuss the generator connection process given in NER and applicable in NEM to give you a brief overview of the generator connection process in the national electricity market. So let's say there's a generator connection proponent who wants to connect. So this is the process that they have to follow. The first stage is pre-feasibility. This is basically the feasibility study level, and the proponents can start discussing with the network service providers, getting data, and that is pre-feasibility. And the second stage is connection inquiry. So in this stage, the connecting party can submit a connection inquiry to the network service provider, and the network service provider has the obligation to respond within 30 business days. So what we would have in this connection inquiry response is usually they have like high level connection arrangement, and it will also say whether there's sufficient capacity in the network for the connection, and it will also have like technical study requirements and technical performance requirements that the plant will have to meet. Those are the main items in the connection inquiry response. But apart from that, I mentioned about the PIA, preliminary impact assessment. It is also part of this connection inquiry stage. And one more thing we usually provide during connection inquiry is technical requirements, and sometimes things like harmonic emission limits, fall levels, basically the technical requirements that they have to comply with. So that's about the connection inquiry. And the next step is, after the connection inquiry, if they want to go to the next step is connection application. During this stage, actually, the generator connection party will have to provide number of documents to the NSP and AMO. So it is basically during this stage, they have to provide the GPS document or the Generative Performance Standard document that I mentioned previously, and they have to also do intensive studies to demonstrate that they can meet the technical requirements given in that GPS. So that's about the connection application stage. I think there's some background.
Yes, that's right. Can you all please mute your mics, please? Excuse me, members. Please, can you all mute until the presentation is over?
I think it looks good now. Seems to be good.
Yes. There's one more person is not muted, which is.
I think it's all good now, Soti.
Yeah. All right. Okay. Thank you. Please continue. Yeah. Okay. Thank you.
So we were in the connection application stage. So as I mentioned, once they submit the connection application, and which includes the GPS document and the intensive GPS compliance assessment, highlighting that they can meet those technical requirements. Usually AMO and NSPs will review those, and once they are happy, the connecting party gets this one called the offer to connect. The FIA, the full impact assessment, is also part of this application stage, which I mentioned during my explanation on system strength. So after the connection application, they get the offer to connect. And then after the offer to connect, they can go and start constructing their plant and prepare for commissioning. And before they commission, they have to achieve generator registration. So what happens is, during the generator registration, usually in the connection application stage, these plants, they don't have detailed design. The models are sometimes usually high level. So what happens is, when it comes to this construction stage, they have the detailed design and the detailed models. And during the registration, we usually check whether this final detailed design of the plant can meet the agreed GPS during the connection application stage. And then AMO grants the approval for registration as a generator. And then only they can start commissioning. Again, generator commissioning in Australia the process is given in MO, and basically it's a staged process. After generator registration, they can start. If it is a renewable generator, usually they have to start this testing with like one inverter, and then let's say it's a 100 megawatt plant, there will be like 3-4 stages, and each stage they have to do number of tests to demonstrate that they can meet the GPS. And one key item is checking the model performance, checking the actual plant performance against the model performance. So basically they have to overlay the plant performance and the model performance for that stage to be approved. Then we call those stages hold points. And once MO and MSP is happy with that hold point testing with the limited generation, they can move on to the next stage. Similarly, they will progress in the commissioning up to the full capacity. And then after completing the full commissioning, within like 3 months, they have to produce a document called R2 report, R2 validation report, which will include all the details, whether they can meet the performance requirements, whether the models align with the actual plant. So that's the final report. So this is basically the generator connections process applicable in the name. I thought of explaining this as it might be helpful for most of you. So that's all I wanted to cover in the presentation today. Happy to answer any questions that you might have.
Thank you, Dr. Kanjana. So we will wait for the questions from the floor. Please, all of you, welcome to put up your hands and ask some questions, definitely.
Hi.
Hi, Ashini, we can hear you.
Yeah, just regarding the grid following systems. So do they have the black start program capability?
No. No,
So,
they don't basically, Ashini. They will struggle to operate without that grid voltage waveform. So they rely on the grid voltage waveform as if they cannot track the angle, or if there's no grid voltage waveform, they struggle to operate. So grid following, they cannot provide any black start services.
is that on any investigation stage, or it is definitely saying no, they cannot?
It is definitely definitely they cannot do that. But grid forming, on the other hand, as I mentioned, they are like a voltage source, so they can form their own grid. So it's like a synchronous machine. So it is expected that grid forming inverters can provide these services. But again, as I know, this has been tested in microgrid type environments. I'm not sure whether it has been tested in large networks, but what I have heard from a number of people is it is quite possible. There are like number of challenges like transformer energization, how they can do that. There are a number of challenges, but if we stage and plan that properly, it is expected that these grid forming inverters can provide these services in future. And actually, this is considered as one drawback in grid following inverters. Their nature of trying to follow the grid voltage.
All right. Thank you. Thank you very much.
There's a question from Amila Fernando. Come on.
Thank you, Dr. Kanjana, for the insights given on this presentation. Hello. My question is, now we are aware on the support services that need to be provided by the operator. So the cost of investment and the operation are being transferred to the customers or being borne by the government?
It is passed to the customers at the end, I think, because I think that's what happened even in a conventional network as well, because it's not only about managing the supply and demand, as I mentioned. Even for the operation of a normal power grid, for the reliable and secure operation, they need to have these services like, for example, FCAS, frequency frequency control services. I mean, there's no difference between who pays for them in a network with renewables or synchronous. I think my understanding is even in the current setup without much renewables, the consumers has to pay at the end for those services.
Okay, thank you. My second question is, when you consider the initial investment by the investor and these additional costs for the support services, even with that, these renewables are economical when compared with the traditional systems or not? Because I think this part of the cost equation is a bit hidden from the initial investment.
Yes, I should say, Amila, I mean, I'm not an energy market person to comment on some of these economics related items, but my understanding is even with those, you are seeing like we cannot, I mean, it's hard to continue to rely on fossil fuels. So I don't know whether you are based in Australia, but we have seen the issues that we faced during the last few months due to the price increases in coal and general gas and all the fuels. So when we consider that one, the cost of renewables are declining faster. So although sometimes my understanding is in the short term, it may not be very economical sometimes, but in the long term, because there are other things like how the market is set up as well, how based on how the electricity market is set up, at least in Australia right now. Usually, although we have renewables, the final market clearance price depend on the last generator dispatch. So if that last generator is a gas or a coal generator, we still have to pay that. But if we have more renewables, what happens is that final generator clearance price will be defined by renewable generators. So it could be that's how I understand that in the long term, renewables could lead into cheaper electricity prices. But again, I'm not, my area is planning and power system side of it. I'm not, I don't know much about the market function, but this is my understanding based on my general knowledge.
Thank you very much, Dr. Kanchan. Thank you.
There's another question from Manjula, okay, that is she has put on the chat. Thanks for the presentation. I'm non-electrical engineer. Do you think Sri Lanka, we have opportunity for grid split or partitioning and to import, export from one region to another? And will it be advantageous in the penetration of high VRE? So
I think if she meant by, I don't know, sorry, whether it's a lady or a
yeah,
gender,
looks like
I don't know
lady.
that. Yeah, but my understanding is if she refers to various regions within Sri Lanka, I think it is important. As I mentioned, like renewables are highly dependent on the resource availability. So sometimes in some part we might have high solar generation. So in some parts we might have high wind generation. So if we can improve the constraints for energy transmission, it will definitely help. Otherwise, sometimes even if you have high generation, high solar in one part of the network, if our transmission network stops it from being transferred to the other side, it is a problem. But in traditional power networks, I think all the transmission systems are also developed around where generators are and where loads are, but it has to be changed with the renewable rich networks so that energy available in one region can be easily transferred to the other regions. There's a second question as well. What is the reason of less renewable energy in east side of Australia when it comes to South Australia? Okay. So I think, yeah, actually South Australia is leading in terms of renewable energy penetration in Australia. Basically, I think, as I mentioned, I showed you the figures on total NEM. As I mentioned, like we have only reached up to like 61.8% of instantaneous renewable penetration levels in the NEM, but I think Australia already recorded 100%. South Australia already recorded 100% instantaneous penetration levels few times already. Actually, they compared to other states, South Australia is actually leading. That is correct. The main reason is they have lots of wind generation. So that's the key reason. They have solar as well, but there are lots of wind farms in that region. So that's one of the reasons. That's the answer to the first question. Second one, how about hunting between inverters of grid forming inverters? Since they follows the grid. Actually, grid forming inverters doesn't follow the grid. Grid following inverters follow the grid, and these interactions, I think things like hunting, there are ways to manage those concepts like droop, for example, which we commonly use in voltage control. They can be applied into concepts like grid forming inverter operation as well, when there are a number of grid forming inverters, nearby grid forming inverters trying to operate. So there are ways to manage that. Next one, FCAS raise services cost to generators. Lower services go to consumers. I don't think I really get that question. So the FCAS raise services cost goes to generators.
Where is this question coming? I'm not seeing this.
Probably it's a comment. It's in the chat. I think it's a comment, Soti. I think it's a comment.
Oh, right. Okay. There was a comment from Manjula. So she looked like she's a graduate from Peradeniya and recently graduated from the ANU. So
good to know that.
Did the doctorate, PhD at ANU. Yes. Thank you, Manjula. Yeah. And I don't see any other questions in my chat box. Please, all of you, one of the thing what we expect is all the young engineers participating be active on the forum and come and ask some questions from our speaker, please. And also, is it all right if I ask you to turn on the videos to take a screen snapshot at the end of the meeting? Can you all wait and turn on the videos for us? All right. Okay, we'll wait maybe another 1 or 2 minutes for Okay, thank you. So before going to the vote of thanks, so can I just ask all of you to turn on the videos and we can take a screenshot for us?
It's good if Kanchana can stop presenting. Thank you.
Yes.
Yeah.
Then we can get a full screen. Yeah, okay.
How are you getting? 47 people are there, or how many faces we have?
Can't get everyone at once. Give me 1 minute.
Yeah.
Okay. Just please hang in there for 10 seconds.
Yes.
Yeah, done.
Second level also, we have covered everyone.
Yeah.
All right. Thank you, Rasika. Thank you, ladies and gentlemen, for owning the video. I think look like Dr. Kamal also here, look like our president, IESL. All right. Let me invite our Vice Chair, Engineer Rasika Gunavatana, to give the vote of thanks on our behalf of IESL New South Wales chapter.
Thanks, Odi. So I again say good evening to Dr. Kanchana and IESL New South Wales Chair, Sodhi, and our committee members and ladies and gentlemen. So it is a great pleasure to propose the vote of thanks on this occasion on behalf of IESL New South Wales chapter. Let me first and foremost thank our distinguished presenter, Dr. Kanchana, for delivering this informative and I think it's a timely presentation. And we are grateful for the time and effort you took to share your thoughts and experiences with us. Also, I would like to express my sincere thanks to Dr. Manasi, our New South Wales Chapter Secretary, and Mr. Chamila from IESL headquarters for the communication work and support extended in setting up this Zoom event. Also, I would like to thank our wonderful audience. That was a very great turn up today for your interest in the presentation and valuable questions. Last but not least, I thank our committee members for the IESL New South Wales chapter who worked behind the scenes and for your cooperation in making events like these possible. One more thing before closing, it's a small reminder about our upcoming face-to-face events. Well, this is basically for our Sydney audience. IESL New South Wales chapter is organizing a Young Engineers Day, which this time would be a career guidance expo, which I'm sure it will be very handy for young engineers. This will be on 9th September 2022 at 5:30. This will be held at Engineers Australia Auditorium in Sydney. Well, I can encourage all young engineers who live in Sydney to participate. We'll send some flyers. We send one flyer, but we'll continue to send. Also, our annual engineering convention and gala night happening in this October. So again, watch out for our flyers for more information. Looking forward to seeing you all in our next presentation. Good night, everyone.
Thank you very much, everyone.
Thank you, everyone. The floor will be open for some more time, maybe another 10 minutes. So somebody want to have a chat among us, please go ahead and to discuss.
Dr. Kamal Laksiri also here.
Yes, he has just sent a message. He has come for the last part of the presentation, maybe, but so he has sent an
yes,
message here.
Thank you for arranging this event, and I think many members from Sri Lanka also joined today. So thank you for arranging.
Yes, we can see that, Dr. Kamal. Yeah.
It was about there was about 70 registrations and about I think 40 or 45 were from Sri Lanka.
Looks like a lot of people has come from Australia as well.
Yes. Yeah. It's good to see.
Yeah, I think maybe the interest is because the power bills are going up, so that's what everyone walk in. Okay. Dr. Kamal, here also the power bills are going up. We have a power crisis almost.
Yeah, this is our topic today.
So I think that's a reason. There is a
committee chairman is also here today. Engineer Kosala.
Sorry.
Our electrical engineer section committee chairman, Engineer Kosala, is also there.
Okay. All right. Okay. Hi, Kosala. Yeah. There is also one last question came in from Ishi. Okay. Can you brief how frequency and voltage are controlled in current MEM systems? Kanjana?
Okay, let me, is it in the chat?
Yes, it came on the chat just now.
Let me see. How few brief frequency and voltages are controlled in current MEM system? I think we, in terms of frequency control, I think we still have, we still have some conventional services as well. Like, we still have a number of synchronous generators in operation as well. So we still have those conventional generators providing some support. But in terms of the frequency support during the past few years, I think we had lots of battery storage connections. So they also contribute to FCAS or frequency control services in the recent years, but we still have other services as well. In terms of the voltage control, we again have conventional devices still, like there are SPCs in certain critical locations for voltage control. So we still have conventional methods, but as I mentioned during the presentation, like in terms of voltage control, if inverter-based renewables are sized properly, they can actually help compared to all these other services. Like if they have headroom to provide reactive power support, they have that reactive power capability. And if most of the renewable generators here in NEM, they operate in voltage control mode, which can effectively utilize the reactive power capability. And under the national regulatory rules or the technical requirements in Australia, there's certain amount of reactive power capability that they have to provide, and certain voltage control capabilities that they have to supply. So in terms of voltage control, renewables are not too bad. But apart from that, for general voltage control, we have these devices like SPCs, like in other parts. But again, in this transition, we are seeing some innovative ways to tackle these problems as well. For example, like traditionally in traditional networks, like when there's a network issue, even a transmission planning type issue, we used to go for traditional methods. But now I think at least there are things happening on the trial level, how we can use batteries to provide some of the traditional services, even voltage control services in certain part of the grid. So there's transition, and I think there will be lots of new things happen. It's an interesting time in this industry in Australia as well, actually, and there's a good demand for experienced people in this particular area as well. I should mention that as there are lots of interested people today, in Australia, there's a very good demand for experienced people in this particular area as well. And actually, there are not many experienced people with the right skills to support. So it's a problem across the industry as well.
Also, Dr. Kanchana, if you can share your email address or something, if somebody has a question, they can send you an email or something, if that's okay.
Yeah, that's okay. That's okay. Let me include my, anyone can reach me out in LinkedIn. I'm happy to share my knowledge in this area. I will share my email address as well.
I hope everyone
There's
can see the
another
email.
question as well, I think. Please let me know how to select the inverter transformer, core transformer. What are the advantages and disadvantages of using 2-winding versus 3-winding transformers? That's a good question, actually. But the thing is, in Australia these days, we don't have much choice when it comes to inverter transformers. Usually the inverter and inverter transformer comes as a single unit, so usually provided by the same supplier. So usually when it comes to inverter transformer, which converts the voltages to MV side, usually we don't have much choice whether it's a 2-winding or 3-winding. It's basically coming from the manufacturer, same manufacturer.
All right, there were a lot of appreciations came from a lot of the participants congratulating and thanking you, Dr. Kanchana. We are very proud of you. And there was one Ishi, I think Ishi. Okay, she's asking, I think he or she is asking about, yeah, Rasika has put that one, okay. So she's asking, is there a IESL Queensland group? So there is a division operating in Queensland, IESL Queensland chapter. This can be found easily on the website. They have a pretty well maintained website. So if you Google it itself, you can get it. Otherwise also, we can put our number for you to contact. I'm putting my mobile number, Australian number, so anybody has a question can ask me to how to get into the Queensland chapter or something. Yeah. All right. By doing that, any more people want to have some more discussion? How about Mr. Engineer Kosala? Yeah. You have any comment?
Yep. Yeah, Swati, it's very timely topic. Actually, we are also talking about. We have been given a 70% RE target in Sri Lanka. We are discussing about that one. So definitely we can get Kanchana's views also. We are having a lot of discussions these days. We are going to have several public sessions, actually presentations as well. Dr. Kamal also actually really like to take that topic, and so we'll get your help, Swati. Yes.
Yes, all right. Thanks, Engineer Kosala, for your few words and appreciating our effort and Dr. Kanchana's ability. Thank you so much. So I think it's the time to close the meeting. So let us meet again in another occasion on a public lecture series. Thank you everyone for taking your valuable time and coming and joining with us and making this event great success for us. Thank you so much.
Thank you very much, everyone.